Okay. Okay, good morning, everyone. Good afternoon for some of you. It's my pleasure to say a warm welcome to Professor Galina Mirzaeva from the University of Newcastle. She is currently visiting the University of Talca as part of a short stays program from ANID. She has been visiting us since a few weeks ago, visiting also the university Catholics, I don't know, Holy Catholics University in Concepcion. And I hope she can be enjoying the Chilean weather. Okay, today we will have Galina's presentation. Professor Mirzaeva received the Bachelor Engineer in Electronic Engineering in 1990 and the PhD in Electrical Engineering in 1997 from the South Urals State University in Russia. From 2004 to 2010, she was a senior researcher with the CFC Mining in Australia. And since 2010, she has been with the School of Electrical Engineering and Computing in the University of Newcastle, Australia. First as a senior lecturer and from 2017 as associate professor. Her research interests include electric machines and drives, power electronics, and renewable energy applications. From 2009 to 2011 and from 2020 to 2022, Dr. Mirzaeva has served as a chair of the IEEE IS Mining Industry Committee. Galina, thank you very much for accepting our invitation. And now the screen and the microphone are yours.
Thank you very much for the introduction, and thank you for your attention, for the being present at this presentation. I've been very much enjoying the hospitality of Chile, so I love it in Talca. I also very much love my time at Concepcion. So thank you once again. It's been really warm and friendly and nice here. My talk today is has a general title of Advanced Control of Power Converters and Systems. I will start, yeah, okay, just get my, oh, that's better. Okay. My talk will include introduction of the University of Newcastle and research opportunities there. And then I will go through some research topics that are of potential for collaboration between our universities. Okay, so some of you, I think most of the people who are currently online have been to Newcastle, but some people, particularly students, are probably yet to come to Newcastle. So I will explain a little bit about it. So Australian continent looks like this. And the majority of population of Australia live along the eastern coast. So there is just one city after another along this line, and the remaining part is mostly desert. So if you look at the map of the New South Wales, which is the biggest state of Australia, no, not the biggest by population, but not by territory. So that is New South Wales. And the largest city of Australia and this state is Sydney, which everybody heard of. And along the coast, there are also other cities, and Newcastle is about 180 kilometers to the north. So it's only reasonably short drive, so we can enjoy the attractions of Sydney, but we also enjoy being not Sydney. And not Sydney is has some advantages. So first of all, we have very beautiful nature and not very much people. The landmark of Newcastle is this Nobby's Head, which is a peninsula sticking out. So the city of Newcastle starts out there. And here is just one beach after another beach after another beach that we love swimming in. So this Nobby's Head is a historical landmark. This is a fortress that was built in the 19th century to protect Australia. And the fortress was never used because nobody attacked it from that end. So Newcastle really was never attacked by anyone. The Japanese Navy attacked from Sydney Harbour, but not from Newcastle. So now it is more of a museum. And also you can see a very nice promenade that people use for jogging and walking. You can go all the way to the end of this headland. Now, another special thing about Newcastle, and these things we have in common with Chile, is winemaking. So the region called Hunter Valley is really next to Newcastle, and we grow a variety of grapes. And this area is particularly famous for Shiraz and Semillon. Also, they make Sauvignon Blanc and all other wines. So whenever you buy a bottle of wine from Australia, if you decide to do that, while you do it, you have very good wine in Chile, but sometimes people want something different. Just have a look at the label. The chances are that it may be made in Hunter Valley. Now, the other thing about Newcastle is that it is a center of mining industry, not the city itself, but the surrounding area, and also a coal port. There is a huge port in Newcastle suburb where we mostly ship coal to Asian countries. So we produce high quality coking coal, really black rich coal. And this is a picture of a typical open cut mine that again, Chilean people are familiar with. So those two things, winemaking and digging mineral resources and exporting them are very common between Australia and Chile. Newcastle University is unique in Australia. Is located is a very big land. It was donated by a private donor, and the campus was designed in a landscape friendly way, so you cannot see the buildings amongst the trees. And that is nice, but it also creates some problems for people to find their way, particularly first year students, but even people who work in Newcastle University for almost 20 years, like I do, sometimes get lost on the campus. It's really big, and you really need map if you're looking for something specific. The newly built building in Central Business District looks like that. So it is sort of architecturally innovative building, but it's not very useful for teaching. There are only good rooms for meetings at the top 2 levels, and the rest is sort of open area. So we almost never teach there. We have nice meetings and we show it off to our guests. It also looks good on photos. But this is our new representation in Australia. Now, University of Newcastle is traditionally strong in 2 areas. One is control. For controls particularly, it's in the top universities in the world. This rating is outdated a little bit. I forget to update it. We are currently at number 11 or 12 in the world on automation and control. So why University of Newcastle is mixed with such universities as Stanford and Harvard in the top universities in the world? So the reason is there has been a Center of Complex Dynamics and Control, which was directed by Professor Graham Goodwin, who many of you have heard of. He was a good friend of Mario Salgado, a famous Chilean professor, recently deceased, unfortunately. So, and that School of Automation and Control continues to be very strong in Newcastle. The other area that is very strong is power electronics. Not in a way that we are ranked very high according to formal ranking, but if you ask colleagues in power electronics to name a few Australian universities that are active in power electronics, they usually come up with 3. It's Newcastle, it's RMIT, where Professor Graham Holmes is from, and sometimes the name New South Wales University as well, sometimes Wollongong. But Newcastle is in the top of Australian universities that are strong in power electronics. Now, what are the recent current research topics in Newcastle University? So we work on advanced control of power converters, standard, multi-level, and matrix converters. We look at integration of alternative sources to grid, microgrid control, active filtering, and such like things. We also work on electric transportation, more electric aircraft, electric and hybrid marine vessels, and electric cars. And we work with mining industry on various mining applications. Again, you can probably see the list that is familiar to a typical profile of a Chilean university working in power electronics. So this little picture tries to capture the essence of our research in a nice cartoony way. Now, before going to the research topics, I will introduce some research opportunities, and this will be of interest to potential PhD students who want to spend time in Australia. So you can apply as an international candidate for PhD study and scholarship in Newcastle. The two first requirements are must, so you have to satisfy those. It's good English proficiency 6.5 or higher, and master's degree by coursework or research. In addition to that, the two other requirements give you extra points, and usually the students with highest score get the scholarships. So research experience is one of those things, which is the number of years in research position after completing master's. So a student who completed master's and works for a year as a research assistant, for example, get a score on research experience. And then research publications. Research publications count as following. Conferences, international conferences give you 0.5, and international journals give you 1 point each. And maximum is 6. So if you have 12 conferences, you get the maximum score, or you have 6 journal papers is sort of the same. So these are the requirements. So the top students only get the PhD scholarship, but alternatively, and this is what I really want to establish between our university and University of Talca and Concepcion Catholic University as well, is the dual doctoral degree. So what it means is that a student from Chile goes for 1 year to Newcastle, supported by scholarship, and spends the remaining time in Chile. And vice versa, a student from Australia go for 1 year in Chile, and 2 years they spent in Australia. 2.5, we have 3.5 years for PhD study. And then at the end, they get PhD degrees from both universities. So we can start by individual students, and if we sort of establish a stream of students both ways, then we can have a contract, sort of a bulk between the two universities for this program. So these are the things to think about in the area of exchange of students. Now I go into the research topics, and again will be open if you want on the go to ask questions, or you want on the go to ask to give more detail or to skip something. Please feel free. So the 4 topics that I'm going to talk about are advanced control of power converters, then matrix converters, specifically microgrids and mining applications. So advanced control of power converters. This slide shows you a typical feedback control architecture. There is a plant, the object or the system that we're trying to control. And there is an input which usually represents a reference, and we want our plant to follow that reference. In order to do that, we put a controller in front of it, and then we close a feedback around controller and plant. So the feedback may be just direct feedback or may have feedback elements such as feedback filter or something. Well, in power electronics, this is complemented by a few extra elements because power electronics control system is almost always hybrid because the plant in power electronics is a continuous time element. For example, electric motors, resistor inductor, and or LCL filter, something like this. But the control is implemented in discrete time. So you need some interfacing between the continuous time and the discrete time parts. And this interface includes zero order hold and analog to digital converter. So analog to digital converter is easy. You have output, and at sampling instance, you translate it into the numbers using the ADC. But for the zero order hold, this is kind of approximation. So if you think about what plays the role of zero order hold in power electronics, so it is a power converter that produces PWM. So the actual element here is not zero order hold, it's PWM. It is a train of pulses, but the train of pulses is designed in such a way that it produces the same volt seconds as what you want from a voltage that will be held for the entire duration of the cycle. So zero order hold is approximation in most cases. For model predictive control, it is directly correct. Zero order hold is the element there because the voltage is held for the entire duration of the period. But for PWM, it is approximation. Now, the history of discrete time control is summarized on this slide. So it started with the sampling theorem by Nyquist. Then the difference equations were introduced, Z-transform, state space approach, optimal and stochastic control, Kalman filtering, system identification, adaptive control. And the most recent developments are usually associated with model predictive control. So in theory, it started in 1980s, and in 2000s, it was introduced to power electronics. Now, what are the challenges for control in power electronics? The biggest and probably the most important challenge is limited time. So we typically have switching frequency of 10 kilohertz, which translates to 100 microseconds period. And that is all we have to complete all the control calculations. And people often say, but the computational power gets better and better every year. But if you really look at this computational developments, it's not entirely true. So if you lived as long as I do, you may remember the times when Intel processors were getting faster each year. So 1 year it is 100 megahertz, next year it's 200 megahertz. So processors really were getting faster and faster. But in the recent years, the clock frequency of processors reached saturation. So you will get 1 gigahertz, you may get 2 gigahertz, you may get 4 gigahertz. So that is the range where they're currently working. And gigahertz is nanosecond period. So when you're in nanosecond period, you do not have much to improve on. So the clock frequency is not really getting that faster. And for real-time processors, the typical clock is in hundreds megahertz range. So why the processors are getting better? It's because of the more efficient parallel processing. So they are trying to parallel the processes, and that way they achieve faster calculations. And the same for real-time processing. So it's now not about the clock, it's about whether or not you can split your algorithm into parallel processes. If it is efficient, if it can be paralleled, then you get faster calculation. But other than that, you do not get much more from year to year. And that means that the limited time will remain a challenge for power electronics. And it will become even a worse challenge or bigger challenge because the devices are getting faster. So the wide bandgap devices are now operating at 10 microsecond period and maybe 1 microsecond period in future. So your time available for calculation is getting much less. So in order to make the control calculations more efficient, we use special tricks in power electronics, such as cascaded control, one loop inside another, frame transformations, axis decoupling, and other things. But in majority of cases, power electronic system is controlled using a traditional PI because it works every time and it takes very little calculations. How about model predictive control? So many of you work in this space. Here I just review or sort of remind you of the classical current control, predictive current control. Typical power electronics load includes resistor and inductor, so it is a first order system. You predict the current using the model where coefficients A and B are constants, and then you form a cost function, traditionally based on the current error. So the predicted current is compared to the reference current. And then you go through all possible switching states and calculate the cost function for each one of them. And then you choose the one that minimizes the cost function. So that is the classical approach. We can slightly change that without changing the principle. What we can do is the following. So how about we use the first equation, and since the idea is to make the predicted current close to the reference, how about we equate the predicted current to the reference, and then we find what voltage is needed for that. So I calculate the voltage from this model that is needed to bring the measured current to the reference current in one control interval. And then instead of comparing the currents, I compare voltages in the cost function. So that reference voltage can be compared to all available voltages from switching states, and the cost can be calculated for each switching state, but based on the voltage rather than current. So many of you are familiar with this alternative formulation of model predictive control. And how does it compare to the original one? You can actually, by substitution, show that the cost based on the voltage is equal to the cost based on the current times 1/b squared. So they only differ in a constant coefficient, which means that if you compare switching states using one cost or compare switching state using the other cost, you get the same optimal state. Oops, okay. But this alternative form is advantageous in two ways. First of all, it reduces the number of switching states to check because you can immediately see which ones are the closest ones and only find a cost function for those. But the other important advantage is that it allows you to represent model predictive control as a classical feedback control architecture. So the first equation, calculate the voltage reference, is my equation number one. Reference minus A divided by B. So that's this part and A. And then this is choose the closest voltage to the reference. So what it tells you, if you look at it, is that model predictive control in a classical form is actually not a particularly good control because it has a high gain here. It has a feedback gain here. But basically, it is a proportional controller. There is no integral part in it. So MPC actually is equivalent to a proportional control with high gain, followed by a nearest neighbor quantizer, which chooses the voltage approximately equal to the one that you want, which means that modulation part of MPC is not also very good. So you do not expect a good performance from that because there is no integral action and there is not exact reproduction of the reference. This is bad news, but it's also good news in a way that once you understand precisely where the problems are with MPC, you can address those problems. So what can be done, and this is one of the possible ways to improve MPC, is to design an optimal control in MPC sense, which means that it's based on the cost function minimization, but in such a way that it works with disturbances and its objective is to minimize the disturbances on the output. So essentially, you include integral action in this control so that in the presence of disturbances, in the presence of errors, you still do not get any steady state error. That translates into optimal control shown here as two blocks. One part is in a forward branch and the other in a backward, because it is designed in NG wind-up form. And that control removes all the issues with the lack of integral action. So the other effort can be spent on the modulator. Instead of nearest neighbor quantizer, you can run a feedback around it and turn it into feedback quantizer. Feedback quantizer, if it works at a rate faster than the main control, gives you approximately PWM, but with a different harmonic spectrum. And it performs much better than the nearest neighbor quantizer by its own. So, oops, again, it's my Mac computer does that. Okay. There are different options there. For example, the optimal control can be designed based on Kalman observer theory in polynomial form or state space form. So our previous research was focused on polynomial form mostly, but now we're working on a state space form. Still MPC optimal control, but with elements of Kalman filtering included. So if using polynomial form, you can end up with high order transfer functions, and they can be represented as a parallel connection of second order blocks for better implementation, but also for better performance. Then additional computational advantage can be gained from delta implementation rather than shift implementation. In feedback quantizer, instead of a simple feedback, you can design a special feedback filter that gives additional desired properties, for example, selective harmonic elimination or suppression of mechanical resonance. Or you can even use PWM. So you can put in the structure instead of feedback quantizer PWM, and it will be still MPC, but it will be MPC optimal control with PWM. So as I mentioned, we currently work with a Kalman observer embedded in MPC structure. And the biggest issue with the Kalman observer is how to design the gains, because if you look at the Kalman here, it's really very unclear how to do it. Most of people do it by trial and error. We came up with an intuitive but sensible design of Kalman gains, and that can be that design can be done, for example, based on pole placement and other things that are going along these lines that we can potentially collaborate on. Here are the example of the performance of the advanced control compared to the conventional control, and I put PWM in both cases, so it is comparable results. The conventional control has very good performance, but the advanced control beats it, and you can see it in transient, for example. It's really good transient, and you can only get it if you have the parallel implementation of the second order filters with delta combined. And the tracking error is better, which is hard to tell, but it can be shown comparing with a reference. So if there are no questions here, or if there are, please ask now. If not, I'll just move to the next, and you can save the questions for the end. So matrix converters is my current research, and I know that University of Talca has done a lot of research in this space. Oh, there is a chat. Okay. Any questions right here? Okay. Okay. All right. Okay, matrix converters. So why people use matrix converters? They use it for direct conversion from one AC to another AC, voltage and frequency. There are options of matrix converters for DC, rectifiers, and so on, but I will be talking about the classical three-phase to three-phase matrix converter. And traditionally, AC to AC conversion is done in two steps, rectification and then inversion, and the DC link in between. DC link decouples the two parts, and it's very good to have DC link from the control perspective because it's very easy to design control. But DC link is also the biggest element in the system, and you know how big the DC link is. It's like 2 capacitors of that size. So if you take the DC link away, then you obtain a significant reduction in weight and size. And matrix converter does exactly that. So by removing the DC link capacitor and further optimization of the structure, a 20 kilowatt drive was fit in 1 liter volume, including heat sinks. So that is a very, very small drive. And well, first question may be, okay, there are still capacitors there. You replace the capacitors with capacitors. How does that work? So students usually ask that question first. These capacitors for the LC filter are really small. So the LC filter takes usually very small part. In our matrix converter, University of Newcastle, the capacitors are under the printed circuit board. They're really tiny. Okay, so once such a minimization is achieved, which applications benefit from that? The first application is aircraft, of course, where every kilogram of weight is cost as gold. You really want to reduce everything on board the aircraft. But other types of other ways of transportation can also benefit from that, because matrix converter can be, for example, embedded in a wheel. So you have the full drive integrated in a wheel, and does not take much more space than the wheel on its own. So it is a very promising converter for electric transportation, as well as other applications. Now, the inherent limitation with matrix converter is the limit on degrees of freedom. So what I mean by that, if you convert input voltage into output voltage using the switching matrix or transfer matrix, then at the same time, you convert the output current into the input current using the same transfer matrix, but transposed. So there is no independent control of the output voltage and input current. When you apply switching state, it does both. On the other hand, there is redundancy in available switching states. The same voltage can be achieved by using different switching states. And we typically choose such switching states that are very helpful for the input current as well. So as a result, matrix converter has 1.5 full control. You can achieve 1 magnitude modulation index, and that modulation index applies to both voltage and current, and 2 independent angles, angle of the output voltage and angle of the input current. And you either can make the full voltage, magnitude and angle, or the full current, magnitude and angle. The other quantity will be only angle that you achieve. So why this is a limitation? Typically what we want to control the output, because output is our load, and we want to have unity power factor at the supply. And using the angle of the input current, we can exactly achieve that. However, the limitation comes when you want also the active damping. So the LC filter that you have at the input of matrix converter is a resonant filter. You do not want large resistance here because that takes the efficiency. If it is a small resistance, then it is lightly damped filter, and lightly damped filter resonates. So what you want from a control is to also achieve active damping. And the limitation now comes that you cannot independently control input current if you're controlling output voltage. So how people do that, what they do about it? This is a conventional control of matrix converter with a closed loop current control of the output, magnitude of the voltage and the angle of the voltage are implemented in closed loop, and the angle of the input current is implemented in the open loop in such a way that the unity power factor is achieved. There is no active damping here because it's open loop angle. Now, model predictive control is actually very suitable strategy for matrix converter because it is able to achieve both control objectives simultaneously. So if you have the total cost function that is built from the output current error and the supply current error, so the supply current is here on the grid side, with a weighting coefficient, then you can simultaneously achieve the trajectory, the desired trajectory for the output current, and also suppress the resonance to some degree, because you're trying to push the supply current to the reference, which penalizes for any deviations. So you can get the unity power factor and active damping with model predictive control. So this is how it usually works. There is a model prediction, power balance, model prediction, and the cost function minimization of the total cost function. Where is the limitation here? The limitation is that the two control objectives present in the cost are often contradicting each other. So this switching state that minimizes the first one is not the same as the one that minimizes the second one. So you're always trying to find a compromise. So if you gain better performance on the supply, then you sacrifice performance on the output. This is inevitable. This is the compromise nature of model predictive control. So currently at the University of Newcastle, we came up with an idea which removes that problem. So what we are doing here, we are running dynamic control on the output in closed loop, dynamic control on the input, also in closed loop, using Kalman observer approach. And then we have a reference generator based on power factor and power balance that produces such references to both controls that do not contradict each other. So that clash between the control objectives is eliminated. And this is what we're currently working on. It is ongoing work. Here are some simulation results, because we don't have experimental results yet. This is the traditional control, PI with SVM. And you can see that the output current performance is very good, very clean, and following the reference nicely. But there is a resonance excited every time the load changes. And that is due to the input filter resonance. Model predictive control operating at the same switching frequency does good job. You see there is no resonance here. There is very little, but almost none on the supply side. There is a less quality of the output side, but still reasonably good. But total harmonic distortion is not as good for the output, of course. Then the version of model predictive control modulated MPC is implemented in the third case. Modulated MPC is reducing the need for very short switching period, because it implements good suppression of the resonance and good performance of the output. But our proposed scheme that is based on the Kalman observer and on this reference generator is better than MMPC. So you can see very clean. This is the real power at the supply. There is no resonance at all, no resonance at the supply, very clean current at the output. So we are working on this now, and experimental results are yet to be obtained. Now I move to the next topic, distributed control of microgrids. I don't know how many people work in microgrids, but some do. I'll go briefly through this topic. Okay. So if you have a reasonably small microgrid and you want a practical solution, then the first solution that comes is the so-called master-slave control. Master-slave control is very simple. So what is the idea here? You have one voltage control converter, typically connected to battery and capacitor, and its objective is to keep the voltage of the microgrid at the constant voltage and constant frequency in case of an AC microgrid. So this is what it does. It runs the voltage control loop, and inside there is a current control loop. And in order to produce that voltage at constant level, constant frequency, it requires current, because the load changes all the time. That current cannot be supplied by this converter alone. It divides the current reference into its own current and into the references for other controllers Other distributed resources are connected to the grid via current control converter, and they receive the current reference from the master, and they only inject the current according to this reference. These converters are also known as grid forming and grid feeding. So there is one grid forming controller, master, and there are grid feeding controllers, slaves. So this scheme works very well. It's very stable, very simple. Where is the problem? The problem is that it does require high bandwidth communication because the references have to be passed to the slaves at very fast rates because the load changes all the time. There is also requirement for the low bandwidth communication to collect the data from the distributed resources. For example, for harmonic compensation, for unbalance and such like things. So that communication is usually not desired. What people do to avoid that? They use the droop control. In droop control, you have all the converters connected via voltage control or grid forming. So all the converters become grid forming. They control the voltage at their connection point in such a way that droop characteristics are maintained with respect to real power and reactive power. So depending on how much real and reactive power they inject, they vary the magnitude and they vary the frequency. But because the voltage and frequency change, you need secondary control to restore that. So secondary control level will be bringing the voltage, magnitude, and frequency to the reference all the time. It uses bidirectional low bandwidth communication, which is better than high bandwidth. And that works very well. And this is probably the most popular and common control strategy for microgrids these days. However, there are still ways to go around that. And what we propose at the University of Newcastle is a current-driven control. Current-driven control is kind of version of master-slave, but it does not have any communication at all. It is not droop control because voltage is kept at constant and frequency is kept at constant. And that is achieved by the master controller, the grid forming converter here. But the other slaves, the grid feeding converters, they do not receive the reference by communication. They do not send the information back to the master. What they do, they deduce all the information they need from the measured current. So they measure current downstream, and from that, they work out what reference should be applied to main current and to unbalanced and harmonics components. So for example, if you have a microgrid with 4 identical converters on the current control, the grid feeding converters, then what you want is each one of them will take 1/4 of the load current, whichever load current is. So the load current changes all the time, but each one has to take 1/4 of that. How you program them? So the first converter closest to the load measures the current and supplies 1/4 of what it measures. So 1/4 is taken. In the remaining current, there is only current for the 3 converters. So the next one measures the current after itself, takes that as a reference and produces 1/3 of that. 1/3 is 1/4 in the total. So the two guys took 1/4 and 1/4. The remaining part is 1/2. The next converter takes the measurement and produces 1/2 of what it measures. And the last one produces all that it measures. So the control structure becomes like this. So the D is the share in the measured downstream current, 1/4, 1/3, then 1/2 and 1. It looks initially, and from the first look, usually people say, but there is an algebraic loop. You take the reference from your own current. You cannot have the reference from your own current. But it's not algebraic loop. Mathematically proven is that it is a triangular system. So you can resolve each individual reference. And in fact, it works together, and it can be programmed in such a way that the dynamics of all grid feeding converter is identical. For that, you need to program the control gains in a certain way. So in our example, the first gain is K independently selected. The second one is 3/4 of that, the third is 2/4 of that, and the last one is 1/4. And that compensates for the following fact. So if you look at the transient performance, say that the load current changed from 0 to 10 amps. 1/4 of that has to be taken by each converter. So the first converter closest to the load receives that as the reference, 1/4. And its dynamic response is this black line, exponential response. Then after you subtract that current from the total load current, then multiply by 1/3, the reference for the second converter has this nose up here. You see it's elevated at the beginning, but its gain is also less. So if you apply the lower gain to the more sharper reference, you'll get exactly the same dynamic response. The third converter receives the reference showed by the blue line. It's even more tipped at the beginning, but its gain is less. It has the same dynamic response if you program that according to this formula. And the last one has that as a reference, and the dynamic response is the same. So you can program them in such a way that they have identical dynamic response. And in our proposed solution, the master controller, the one that sits on the battery, does not produce any current other than transient. So it takes the transient because there is some gap here between the dynamics of the converters and the load. So that is provided by the voltage control converter. But then it does not participate in a steady state load sharing. You can use battery, but you don't want to discharge it without a need. So as a result, the complex and intervened microgrid structure is actually equivalent to completely decoupled current control for all participating converters. And that means that the complex microgrid architecture can be replaced by equivalent microgrid with only one grid feeding converter and one grid forming converter. And that has very simple dynamics, very stable in the presence of any load, including the constant power load, which is known for destabilizing effect. It still works very well. So there are some experimental results, and the load, the battery is the blue, and here are the two participating grid feeding converters, and the microgrid voltage is shown on the right. So what are the advantages? You can minimize battery and capacitor. In fact, you can get away without battery. Just use ultracapacitors because the load current is not supplied from the battery. It is very stable. It has a high power quality because there is no variation of voltage and frequency. And because of no variation of voltage and frequency, you do not need secondary control. And you also do not need telecommunication. So it's very economic in terms of resource requirements. Application examples include more electric aircraft and other electric transport, such as boats. So during the COVID, we all had a very hard time. In Australia, because we are regional Australian, Newcastle, so we're not the same as Sydney, we were much more free to go around. So we were able to move within the region. And we partnered with the local industries, the local boat making company that produces fiberglass boats. And we applied our microgrid ideas to a small microgrid on board this boat. So we actually created during COVID this prototype, and we were running it on the river to test. And now we're building a much bigger boat for commercial application with the same principle. And finally, it's mining application example. I have still a few minutes there. I'll go very quickly there. So we work with mining all the time because mining is next to us and because mining has money. So if you apply for mining grants, you usually get it. We have various different collaborative work with mining. Some are very practical. There's not much research there, but some are very interesting. For example, very interesting research was related to common mode voltage elimination in underground mines. Common mode voltage is a big problem in underground mines because in underground mines, there are different electrical standards. So it is required, for example, that the transformer secondary is connected to earth via a large resistor. neutral to earth resistor is in the order of 100 to 200 ohms. It's very large resistor. What it does if you apply it together with variable speed drive. So you have variable speed drive here with diode rectifier, inverter, and the motor. So the common mode voltage can be measured if you connect an artificial star load with large resistances and measure this point. So that is the common mode voltage, because usually you cannot measure it inside the motor. The common mode voltage in this case looks like this. So there is a high switching frequency component, but there is also variation up and down. This is due to the diode rectifier. So that common mode voltage is large. Its magnitude is 1/2 of DC link voltage. And there are always parasitic capacitances inside the motor structure that makes the way for the common mode current. That common mode current flows into the earth cable, back to the transformer, and then on this large resistor, it creates a voltage drop. That voltage drop, so that is the circuit for the common mode current. The voltage drop created by the common mode current is added to the normal AC voltage, and you have the voltage that looks like that. That voltage is really bad. It is a typical conducted EMI issue. If the voltage is like that, you have nuisance stripping, you have malfunction of protection. So it's really bad. It's impossible to work with voltage like that. So what they do in mining, they put the so-called EMC filter, LCL filter in the front, which serves two purposes. It cleans the current, but also there is a capacitive connection to the earth cable, you see? So now the common mode current flows through the earth cable, comes to this point, there is a capacitor. The capacitor has very low reactance to high frequency switching. So the common mode current goes in there and the closed loop is like that. So the common mode current does not reach the resistor, hence it does not create the problem with EMI. However, it creates a problem with the protection, because if you have a fault in one of the phases, the current that flows into the frame is also high frequency switched. That means that it goes through the earth cable, comes to this point, and also goes through the filter. It never reaches the resistor. And this is where it is measured. And this is where protection is based on. So that means that the fault remains undetected. That problem, anecdotally, so we do not have a proof, but anecdotally caused some injuries in underground mines in New Zealand. So we were engaged with mining industry to come up with a solution. We tried different ways, but the best way from our perspective was to eliminate the root cause. The root cause of the problem is common mode itself. So how can you remove the common mode voltage? You cannot do it with just inverter. You need two converters, so you need some redundancy. We propose to use active front end and inverter structure, which is a standard drive used in underground, but a little bit more costly than the standard inverter. And then program the two controls in such a way that their switching is synchronized. And switching is synchronized in such a way that if one of them produces positive common mode voltage, the other produces equal negative common mode voltage. So the common mode voltage are always compensating each other. As a result, you have practically zero common mode voltage. That is experimental measurement. There's a little bit of dead time pulses, but it's very, very small. And effectively, there is no common mode current, so the voltage is very clean. And then you do not need this filter, so you do not need to close this loop. And that means that the fault protection works correctly, because the fault current will go through resistor where it will be detected. So that was very successful. And we worked with equipment manufacturers to implement that solution. So this is all that I wanted to discuss. Opportunities exist in collaboration in all those areas, plus other things if you can think of. And you can always contact me. This is my email. And if there are any questions, I'm happy to take.
Okay, thank you very much, Galina, for the interesting presentation. It's a very, very interesting topic for many of us. Now we have some time for questions. If you have any question, please raise your hand and I will allow you to open the microphone.
Sorry.
There is one question from YouTube regarding the use of matrix converters and microgrids. So they want to know your opinion regarding some benefits that a matrix converter implementation in microgrids can have.
In microgrids, yes, certainly. So what we have there, matrix converters, if you have a traditional AC to AC conversion, which means that you will take your input from AC source. So what are the AC sources? Wind turbines, there are diesel backup generators. So these are the traditional AC sources. But if you look at matrix converters in more broader way, there are DC to AC, there is AC to DC, so all sort of options there. And matrix converters have very good potential because of two things. So they're very compact. Whether or not it is important depends on application. If it is something movable, something that you want to make small and light, then it is an advantage. But the other advantage of matrix converters is very high efficiency. So that applies regardless whether you want small size or not. So very high efficiency of matrix converters is the reason why you would like to use them in applications such as microgrids.
Yes. Marco? Okay. Hi, Galina. I have a question about your experience in applying these controllers. I'm talking about the first topic, but using low switching frequency. Because I've seen your results. Maybe you're focused in high frequency, but my focus is in low frequency. And I'm not sure about how observers works in low frequency, like 100 of hertz. Is there any recommendation from the control point of view?
Yes, I guess. Well, for the observer, if you have low frequency, the biggest difference is that you probably need to model the intersample behavior.
Okay.
So it's no longer, so remember there was zero order hold approximation that I used. Zero order hold no longer stands. So if you want a frequency of hundreds of hertz, then you need to model intersample behavior properly. So whatever voltage you're applying, you need to model what is response to that voltage. So that is one thing. It's not actually very hard to do. We have some work done on that already. So intersample behavior. And the other thing is because the controller and modulator are, yeah, just find that picture here. Controller and modulator are separated. So you have a sort of the reference coming from observer, and then you have a modulator. You can do separate things. So the controller does its job perfectly calculating intersample behavior, but then the modulator can be designed in a way that uses optimal PWM principles. So you can design it so that the number of pulses is minimal for the best possible harmonic performance. I will probably go this way. I will design it separately. If you start combining things in one design, you usually make sacrifices. So it makes sense to have a very well-designed controller followed by a very well-designed modulator and tackle the issues separately.
But in that way, this is like in the opposite way, because the observer will be faster than the controller, something like that.
No, the observer will be on the frame of the sampling interval, but the modulator will be inside that. Yeah.
Thank you.
Well, other people do different things. Yeah, it's possible also to predict the inside the sampling, you know, this optimal pulse width. So there are other ways to go. But my current research is on separating and addressing control objectives on different levels. Yes, sorry.
Thank you very much, Pablo. Someone else have any question? If not, in honor to time, Galina, I would like to ask you your opinion. What do you think are still the challenges to solve in order to have MPC and industrial applications?
Okay, it's a good question. I actually presented a whole paper on this on petrochemical industry conference this year. And I got a response from industry that there is one application already confirmed in industry. So there is one company that uses MPC. It's not, the product are not available on the market yet, but there is a company that started building their drives based on MPC. So the challenges there are exactly what I discussed here. So the traditional MPC is not such a good control. And if you can overcome the issues that the traditional MPC has, then it is a much better control and it is competitive and even better than the conventional one. And if you have advantage, then you can approach industry. So what they want very good performance in the presence of disturbances and errors, because there are always disturbances in industrial environment. They want a predictable harmonic spectrum. So if it is distributed, it's okay because DTC also has distributed harmonic spectrum, but it has to be predictable because they don't want to deal with additional AMI issues. So once you can offer a good control with integral action and disturbance rejection, and when you can offer a modulator with a known spectrum that can be shaped and can be played with according to the application, then it is a great potential for industry application. So in fact, with this, I give an example based on this mining example here. So we proposed the solution based on active front end and inverter. And we tried it with MPC and we tried it with standard PWM. And with MPC, it's actually advantageous because for the same switching frequency, and you achieve 0 common mode voltage with better performance than the traditional control. That's potential for optimization of the pulses, which is better with MPC than with the traditional. So all you have to do now is to make this control good at integral action disturbance rejection, and then be able to shape the harmonic spectrum the way industry wants, to eliminate resonances, to not have interactions with protection, and that's the industrial solution, very good solution.
Great. Well, thank you very much, Galina, for your presentation and all the answers and comments to today. And with this, we are finishing this session. And for the next one, for sure, you will receive an email and also we will inform that in our social networks. Thank you very much, Galina. I hope you can keep enjoying Chile. And
oh yes, yeah. Thank you very much. Okay? Yeah, I was not sure how many people show up, but quite good participation. Thank you. I appreciate that.
Yes. Great. Okay, thank you very much. Have a good day. Let me finish.